Hello, this is Fig, and we're going to be looking at force problems today. And this is a pretty typical force problem in physics. When doing any physics problem, it's very important that you have a clear picture of what's going on in the problem. So working with a sketch is always the first step. So in this problem, we have two boxes. Mass A equals 5 kilograms and mass B equals 4 kilograms. Two boxes are pulled with an acceleration of 3 meters per second squared. Find the pulling force Fp and the tension Ft in the connecting string when there is no friction and when 6 newtons of friction acts on mass B only. So here's a sketch of what's going on. I have two boxes and I have a hand pulling a string, and I have a vector here indicating that the acceleration is in the direction that the hand is pulling. Now, it's very important to understand what physics is. Physics is understanding the rules that the universe around us operates by. It's not math. We use math to solve a physics problem, but it's very important to get the physics clear in your head first. So we're first going to concentrate on what's happening when there's no friction on both boxes. Well, common sense says that if you pull the string, the two boxes will accelerate. That is, they will start moving and gain velocity and going faster and faster the longer you pull. The sketch is important to organize our thoughts and information. So first thing to remember is you should never have any vectors touching an object except for a force vector. So I will put some information on here, but we'll leave the force vectors off for now. For instance, mass A is 5 kilograms, so this is a good place just to jot down that mass is 5 kilograms, mass B is 4 kilograms, and the acceleration is 3 meters per second squared. Now, these are strings, and a force on a string is called a tension. So I'm going to represent the force arrows using a red pen. So what I'm interested in is finding this pulling force here. And I'll put a little red arrow here, and I'm going to mark this Fp. This is the pulling force from the hand pulling the leading string. Now, if this box is pulled with this string, it's easy to see that the connecting string is then going to pull the box behind it. It's also clear that if box B was not here, it would take less force just to pull mass A, the first box. Now, the thing to understand about forces on strings, tensions, is they can only be one size tension on a string at a given time. Else, the string would actually feel different forces on different parts of the string and it would start to stretch. So that is that whatever tension box A feels here on the connecting string, and I'll call that Ft, box B is going to feel the same tension going in the other direction. So right away I have a problem. The tensions are the same size, but they're not in the same direction. So I always like to indicate to myself and to whoever is looking at my work what I'm going to call the positive direction and what I'm going to call the negative direction. In this case, I'm going to call any force or vector going to the right positive. And I'll make a note of that right here on the picture. And I'm going to call any force or vector pointing to the left negative. So that would mean that on this picture, the tension acting on box A is actually negative, and the tension acting on box B will be pointing in the positive direction. So although they're the same size tension, the direction of that force on each box is pointing in a separate direction. Now, when working on this, there's two ways to look at this problem. You could look at it as we could just follow the rigor and use Newton's second law. Well, Newton's second law says that if I add up the forces, it'll be equal to mass times acceleration. But looking at this problem, which forces are we talking about? Well, the standard practice is to consider each object separately. That is, I will only look at the forces acting on box A, and I will only look at the forces acting on box B. So that's really taking a single problem and breaking into two smaller problems. Now, it is also clear that both boxes have to have the same acceleration. If box B accelerates more than box A, this string won't stay tight, and it'll actually, block B will actually bump into box A. Or if box B has less acceleration, the string would have to get longer and longer as the box B lags behind. So the first piece of physics I pick up out of this picture is both boxes have the same acceleration, and the tension force between the two boxes are related just by being in different directions but the same size. So what I'm going to do now is make a picture of box A separately and a picture of box B separately. So down here below, I'm going to take box A, and here is my box A, and it feels two forces. It feels a pulling force, and it feels a tension in this direction. Now, one of my practices I like to use when I'm doing a force problem is if I don't put the negative sign in, if I'm just using the arrow to indicate the direction of the force, before I put any negative signs in, I'll just put arrows on top of these forces to remind me that these are vectors. That is, they have a sign associated with them. They're either positive or negative depending on which way they're going, and I'm just not going to deal with that in the picture right now. And similarly, over here, if I draw a box B, here's mass B. And now, box B has no idea what's going on in box A. As far as box B is concerned, it's simply being pulled by a single string, this rope with this tension. So I'm just going to put that force here. And that's it. That's as far as the forces in this problem. Now there is a weight force going down the boxes, and there's a normal force pushing up on the boxes. The normal force being from the floor, but that's not contributing to the problem. It's not contributing to the problem because my motion is only horizontally or in the x direction. So since I'm only worried about motion in one direction, and there is no friction in this problem, at least for part A of it, I can neglect anything going on in the y direction, the vertical direction. Now, if you put those forces on the picture, you could, it wouldn't be wrong, but it might just, confuse the problem by putting things in there that we don't really need for this. So what I can see is, since both boxes have the same acceleration, clearly box B is the easier problem. So let me first take care of what's the physics of box B. So on box B, when I look at it, so just looking at mass B, I can note the rule, Newton's second law says sum of the forces, which is, we often just write that as F net, net being total, is equal to mass times acceleration of the box. So for box B, this tells me that, well, there's only one force acting on it in the horizontal direction, just Ft, the tension. So I say that Ft is equal to, and I'll put my positive sign in now, so I won't have to put the vector hat on, and that is going to be equal to mass B times its acceleration. Now, notice I'm not worried about numbers here. Numbers are just going to confuse me. If 3 is at the acceleration, is at the force. So I'm not going to worry about putting in numbers until the end. Let me now take a look at box A. On box A, again, I would say that F net is equal to mass times acceleration. But now I have to be careful of signs. There are two forces acting on box A. So I will say that Fp, the pulling force, which is in the positive direction, minus Ft is equal to mass times acceleration. And again, this is Newton's second law. Now, the law is the physics here. That's actually telling us how motion relates to forces. If I have a net force acting on an object, that object will accelerate. That is, the velocity of those objects will increase over time as long as the force remains the same. I can see from the two equations that I have tension in both equations. It's the same tension now. I put the sign in, this one negative and this one's positive, but the same size. And I can see that this equation is obviously simpler, so let's start here. At this point, I'd like to do a little inventory to make sure I have all the information I need to solve the problem. Now, what I'm looking for is the tension here. And I see that I have the acceleration, I have mass b, so I'm good to go. So I can simply put in the numbers now. And I'll do that on the next paper so we have more room. So keeping the problem in front of us, I don't know if it's moved out of camera frame, but I can just, again, I'll copy down the equations here. So for box B, I have the tension equal to mass of the block times its acceleration. And in this case, that's going to be 4 kilograms times 3 meters per second squared. So the tension on the string pulling box B is equal to 12 newtons. Newton being the unit of force. And it's very important that we're working in the correct units. In physics, we like to use MKS units. That stands for meters, kilograms, and seconds. That is, if I stick in meters, kilograms, and seconds, all the derived units will be what I expect. In this case, newtons for force. And I have kilograms, meters, and seconds, so I'm good. So the tension in the string is 12 newtons. Now again, that takes care of the tension for both blocks because it's the single piece of string. Since it's a single piece of string, the tension pulling box B to the right is the same as the tension pulling box A to the left. So now I know I know one of the forces acting on block A. I can use that for the block A equation. So if I come down here and I'll now say, okay, let's take a look now at box A. Box A, I have that the pulling force minus the tension is equal to mass of block A times the acceleration. And I should have been more particular here. I should have actually put an A in that equation. So I don't want to confuse my masses. They are different. So now let me do an inventory on equation A. I know the acceleration. I know the mass of block A. I now know the tension. Now, I've already put in the negative sign, so I got to be careful not to put in the negative sign twice. Since I've already indicated that the force pulls to the left by putting in that negative sign, I will just replace the Ft with 12 newtons when I need to put it in. But before I put in any numbers, let's just rearrange the equation and solve for Fp. Now I see that I only have one unknown in this equation, so I'm good to go. All I need to do is add Ft to both sides, and I get that the pulling force on block A is equal to mass of block A times its acceleration, now plus that tension. And I substitute in the numbers now, and I get that Fp, the pulling force pulling block A, is equal to, that's 5 kilograms times 3 meters per second squared. Now, because I brought the force over the other side, I'm now adding 12 newtons. And I get 15 plus 12, or the two blocks must be pulled with 27 newtons of force. Now, and the problem is done, at least part A. So I have 12 newtons on the connecting string, 27 newtons on the pulling string. Now, it's also useful here to take a step back. We could have actually arrived to this answer for the pulling force a little bit easier, or more directly, if we take another look at the picture. Since there is no friction acting on these blocks, as far as the hand pulling the string, this string is connected to block A. There's nothing special about it. If I imagine I had like a little TV camera on a finger here looking, all it sees is block A. It would take the same amount of force to pull one block of combined mass 9 kilograms as it does with the two blocks connected by the string. So I could have looked at this problem another way. I could have looked at the problem this way. So let's take a look at another view. Another view would be to say that I have a combined mass, MA plus MB, equal to 9 kilograms. And the hand pulling that would have just a single pulling force, FP, and I would say that FP equals MA plus MB times A, or I would get 9 kilograms times 3 meters per second squared equal to 27 newtons, which is the answer we got before. Now, if I did the problem this way, of course, it doesn't tell me anything about what's happening in the connecting string. That is, because I combine my masses, that's good for finding FP, but I would have to break out the forces like I did in order to find out what's happening between the two blocks. So this is known in physics as called isolating the free body. That is, when I look at a system of objects, in this case mass A and mass B, I want to consider each object separately. That doesn't mean they don't interact with each other. As we saw, the tension is the same between the two blocks, and that connected the two problems. But it did make the problem easier to think about. Block B was a very simple problem with one mass with one force, and block A becomes a problem with one mass and two forces. And it's kind of like divide and conquer. I can start with block A, simpler problem, and then use that information, block B, the simpler problem, and use that information in block A. Alright, so that's a very straightforward, simple question. It becomes a little bit more challenging when we add friction to the problem. Now, friction is a force between two surfaces being squeezed together. In this case, the friction is between the floor and block B only. So we can imagine that block B has a rough surface and block A is perfectly smooth, or maybe block A is actually on wheels and doesn't feel any force, any friction. So how does that change the picture? Well, it doesn't change the problem at all as far as the picture goes for block A. But if I do now have another force acting on block B. So if I just look at part B now, I would need to change my picture to block B now experiences a force in this direction, and I'm going to mark that FF for force friction. Now, I'm going to put a little reminder down here that these pictures are only for part A of the problem, and I'm going to go to the same trick. I am now going to draw new pictures, one for block B, one for block A, to do the second part of the problem. So I'll just flip our paper over here. Paper's cheap. I will start a new piece of paper. And I will now do part B of the problem. Now, don't be shy about using paper. The biggest mistake new physics students make is try to squeeze their work in a small space. You want to take the time to organize your thoughts, especially when if you've never seen physics before and suddenly you look at a picture like this, it can be a little confusing. What are these arrows? What's FT, FP? So you want to not mix things up. You want to have a clear idea to see what's going on with each block. So I will now go to block B, part B, and draw block B. So I have mass B. But unlike the previous problem, mass B now feels a force in this direction as well as a force in this direction, the force friction. Well, let me make that clearer. F, there we go, force friction. Now, again, penmanship can also be your worst enemy, so let me just force friction. And let me draw block A again. And here is mass A, and I'll add my force vectors again. So now I have force P and force tension. Now, the way the problem was written with the friction only acting on block B, that's why I've only added force friction to block B. But you can see the strategy if the friction was acting on both blocks. If friction was acting on both blocks, I would need to know the size of the friction acting on block A, but I would just add another force vector for friction pulling against block A. Friction always opposes the direction of motion. So if my blocks are pulling to the right, friction would always point to the left. It always hinders the motion of the object. But this problem stated that friction is only acting on block B. So let's do the problem again, but now I'll set up the Newton's second law with these forces. And it's not any more difficult. I just have to include the forces. So again, note that we had originally called to the right positive and to the left negative. So when I substitute in, this friction is pointing in the negative direction. So again, if I use my vector sign to indicate that I know the net force now is the tension plus the force of friction. Now, this indicates that I haven't put in any signs, but now I'll put in the signs of the forces and take away my vector hats, as I like to call them. And I get that I have force tension minus force friction acting on block B equals the mass of B times the acceleration. Now, the problem doesn't indicate that we have a new acceleration, so we assume that the acceleration is still 3, and we expect these forces to change. In fact, I expect that this tension needs to be larger, or else I wouldn't have the same acceleration, because friction is now canceling out part of that pulling force there. So I'll solve this for Ft, and I get that Ft equals mb a plus force friction. And again, I've already put the negative sign in, so I got to make sure not to put it in a second time. And I'll just put in the numbers. And I have 4 kilograms, 3 meters per second squared, plus the force friction, which the problem indicates is 6 newtons. So 4 times 3 is 12 plus 6. The tension on the connecting string then is 12 plus 6, or 18 newtons. And of course, it's larger than what it was in the previous problem when we only had the 12 newtons. Now, if you did make a sign mistake, and if you got an answer less than 12, that would be a clue that you should go back and check your work and see if there was a mistake somewhere in the math. Because I expect, and I found the tension to be larger when friction acts on the block. But what about block A? Now, block A doesn't know anything about the friction acting on block B, but the tension in the string has to be the same in the connection between the two blocks. So because this tension is larger for block B, it's going to affect the problem for block A. So again, for block A, I'm going to just say that F net, and I'll just put the signs in directly. I won't worry about my vector hats. I have the pulling force, which is in the positive direction, minus the tension, which is in the negative direction, and that has to be equal to mass times acceleration. Now again, note, there's no friction acting on block A in the way the problem was worded, so I have no friction force in this equation. So let's just solve for the pulling force now. I get that Fp equals mass times acceleration plus F tension. And I'll plug in my numbers. Oops, again, that's mass A, that's mass A. So I get 5 kilograms times 3 meters per second squared, plus now 18 newtons for the tension, and I find that the pulling force is equal to, that's 15 plus 18, which is 33 newtons. And there you go. So this is a common early problem in Newton's second law. And so hopefully now you've got a little bit of idea of how to set up a problem with forces going only in one direction, that is either horizontal or vertical. Now, again, the key is to carefully have a picture of the problem in front of you, carefully label the forces so you understand what's going on. Don't put an acceleration vector or a velocity vector. Don't have that touch the objects. You want to reserve the vectors touching the object only for forces, because forces are key when using Newton's second law. It's useful to note the acceleration on the picture, but you don't want to confuse it with a force. Also notice that units are very important because that keeps the information sorted. You don't want to confuse an acceleration with a mass or with a force. Okay, that's our first example problem here on Newton's second law applied to two boxes being pulled. I hope I didn't go too quickly. I hope I didn't go too slowly. And good luck finishing the other parts of this problem in your homework set.